Hello and welcome to this lesson on indices. In this lesson we're going to answer the question, what are indices, before looking at the indice power laws and the proofs for each of them. We will then go on and look at some of the typical exam questions that you will face for the topic of indices. If you want to navigate to the correct part of the video, as always, the links are in the video description. So what are indices? Well, indices are basically notation. They are numbers or symbols that we place in the top right hand corner of another number or symbol that will tell us how many times it is multiplying by itself. For example, if we had a to the power of n, this would be a times itself, n times. Indices are extremely powerful. They're actually more powerful than both multiplication and addition. Let me demonstrate this with a quick example. Say I let you pick any two numbers between 1 and 10 and you picked 2 and 7. And I told you that I was going to let you conduct an operation on these two numbers and the answer would be an amount of money that I would give you. So you want to make as big a number as possible. Well, if you decided to add these two numbers, you would add 2 and 7 and you would get 9, which is good, but it's not great. If you were to multiply these two numbers, you would multiply 2 and 7 and you would get 14, which is better. So multiplication is more powerful than addition. But if you were to use powers, say 7 to the power of 2, you would get £49, which is a lot more money. Interestingly here, 2 to the power of 7 would give you even more money, as 2 to the power of 7 is 2, 4, 8, 16, 32, 64, £128. We can therefore order these three operations in this sort of hierarchy of power, with addition at the bottom, multiplication in the middle, and powers at the top. This is going to be important later as it gives you a quick tip for remembering the indice power laws. Just like multiplication has division, which is sort of its opposite, and addition has subtraction, which is its opposite, powers also have an opposite, and it's called the root. The opposite of squaring something is the square root. The opposite of cubing something is the cube root, and so on. If there is no number on the symbol, like this one, that is the square root. Any other root will have a small number at the front, so this would be the cube root, this would be the fourth root, and so on. The definition of the nth root of x is the number which, when it multiplies by itself n times, gives you x. Therefore, the definition of the square root of x is the number which multiplies by itself to give x. The definition of the cube root of x is the number which multiplies by itself twice to give x, and so on. Always remember that the nth root of x to the power of n equals x. So the square root of x squared equals x, and this cube root of x cubed equals x. When using roots, you must remember that two negative numbers multiply together to give a positive number. Therefore, the square root of any positive number has both a positive and a negative root. This is true for the nth root of any positive number when n is even. The cube root of x and the fifth root of x will have just one answer with the same sign as x. But for any even n, the nth root of x can be both positive and negative. A quick example would be the square root of 4, which is both positive and negative 2. By convention, we take the square root of any number to be positive, and then we use notation like plus minus to show that there's both a positive answer and a negative answer when we take the square root. Remember that you can't take the square root of a negative number. Now let's look at indices on brackets. While not a formal indice law, applying an indice to a bracket is very important, very common, and a very common mistake that many students make at GCSE level. Let's build up from the bottom. X cubed is just x times x times x, and y squared is just y times y. But we can also write x cubed y squared, which would be x times x times x times y times y. This might seem obvious, but it's important when we then apply a power, or an indice, on a bracket. Let's think about what xy all squared really means. It means x times y times x times y. But multiplication is what we call communicative. It means it doesn't matter what order we multiply things in. 2 times 3 equals 3 times 2. Therefore, we can write this x times y times x times y as x times x times y times y. and we could then write this as x squared, y squared. We can see from this example that the power outside the bracket has been applied to both of the symbols inside the bracket. We might, however, also have a number inside the bracket. 3xy all squared is 3 squared times x squared times y squared. So becomes 9x squared y squared. Many students forget to apply this power to the number at the start of the term inside the bracket. Don't do this. Take it one symbol or number at a time and apply the power to everything inside the bracket. Now let's look at the indices laws. I'll first go through the indices laws and give you a quick tip on how to remember them. I'm then going to show you the proof for each one, as I think this really helps students to understand why the indices laws are true. Okay, so here are the 6 indices laws. X to the power of a times x to the power of b equals x to the power of a plus b. If we multiply the numbers, we then add the powers. X to the power of a over x to the power of b equals x to the power of a minus b. If we divide the numbers, we subtract the powers. X to the power of a to the power of b equals x to the power of a times b. If we take one number with a power to another power, we multiply the powers. X to the power of 0 is always equal to 1, no matter what x is. X to the power of minus a is 1 over x to the a. And x to the a over b is the bth root of x all to the power of a, or the bth root of x to the power of a. Both are true. If we go back and look at our hierarchy of operations with addition at the bottom, multiplication in the middle, and indices at the top, this gives us a quick method for remembering the indices power laws. When we multiply x to the a and x to the b, we add the indices. Therefore, if we're operating on the multiplication level for the numbers, the powers drop down to the level below and are added or subtracted. However, if we are operating at the highest level, at the indices levels, where one indice is taken to another indice, we drop down to the level below that and we multiply these indices. Now let's look at a proof for each of the rules. Let's start off with x to the power of a times x to the power of b equals x to the power of a plus b. Well, the definition of x to the a is just x times itself a times, so we could write it like this. The same with b. X to the power of b is just x times itself b times, so we could write it like this. Therefore, x to the power of a times x to the power of b could be written as x times itself a times with x times itself b times. We can remove these brackets because they don't really matter anymore, and this is just one big long line of x's multiplying together, and there are a plus b of them. And this is the very definition of x to the power of a plus b. Here's an example. 4 to the power of 2 times 4 to the power of 3 is just 4 times 4 times 4 times 4 times 4. Here we just have 5 4's multiplying together, so this is 4 to the power of 5, which is 3 plus 2. The next law is x to the power of a divided by x to the power of b equals x to the power of a minus b. Again, we can write x to the power of a as x times itself a times, and x to the power of b as x times itself b times. Then x to the power of a divided by x to the power of b is a fraction with x times itself a times on the top and x times itself b times on the bottom. Let's assume for this that b is smaller than a. We could then cancel all the x's on the bottom, b of them, and we could cancel b of the x's on the top line. This will leave us with a new fraction of x times itself, a minus b times on the top, and just a 1 on the bottom line. And this is x to the power of a minus b. An example would be 6 to the power of 4 divided by 6 to the power of 3. This is 6 times itself 4 times on the top of the fraction, and 6 times itself 3 times on the bottom of the fraction. The 3 6's on the bottom and 3 of the 6's on the top cancel, leaving us with just 1 6 on the top and a 1 on the bottom line, which is 6, or 6 to the power of 1. The next law is x to the power of a to the power of b. Again, we can write x to the power of a as x times itself a times. X to the power of a to the power of b is just x to the power of a times x to the power of a times x to the power of a b times, so we can write it like this. Each of the individual x to the power of a's, however, can be written as x times itself a times. We can therefore see that we have b lots of a x's multiplying by themselves. This is a times b x's multiplying by themselves. So we could write this as x to the power of a times b, or just x to the ab. An example of this would be 4 cubed squared. This is 4 cubed times 4 cubed, which is 4 times 4 times 4 times 4 times 4 times 4. Here we have 6 4's multiplying together, and this is 4 to the power of 6, and the 6 comes from multiplying the 3 and the 2. The next rule is a strange one. X to the 0 equals 1. This is very counterintuitive for most people, and therefore I think seeing a proof really helps. In this proof, we're going to express 0 as some number a minus itself. A lot of proofs do this, expressing a value like 0 in some other way, or multiplying by 1 in some strange way, so you probably will see this sort of thing again. In this case, if x to the power of 0 equals x to the power of a minus a, we can use the second rule of indices to rewrite this as x to the power of a over x to the power of a. This is using the rule x to the power of a over x to the power of b equals x to the power of a minus b backwards. Well, we now have x to the power of a over itself, and anything divided by itself is just 1. So we have x to the power of 0 equals 1. Again, this is true no matter what the value of x is. 2 to the power of 0 is 1, 3 to the power of 0 is 1, pi to the power of 0 is 1, and so on. The next rule is x to the power of minus a equals 1 over x to the power of a. Again, we're going to use a similar trick like we did in the last one. And we're going to write x to the power of minus a as x to the power of 0 minus a. We use the second indice law backwards like we did in the last proof to express x to the power of 0 minus a as x to the power of 0 divided by x to the power of a. We now use the last indice law, x to the power of 0 equals 1, to replace the top line with a 1, and the proof is finished. X to the power of minus a equals 1 over x to the power of a. Anytime you see a negative power, you can immediately move the entirety onto the bottom line, always remembering that it's simply a 1 goes on the top. The final rule is the most complicated, so we'll take this one slowly. The rule is x to the power of a over b equals the bth root of x all to the power of a, or the bth root of x to the power of a. In order to show why this is true, let's just focus on x to the power of 1 over b first. If we took x to the power of 1 over b and put it to the power of b, using the third indice law, this would be x to the power of 1 over b times b. 1 over b times b is just 1, so this equals x to the 1, which equals x. So we have x to the power of 1 over b to the power of b equals x. Writing this out in another form would look like this. X to the power of 1 over b times x to the power of 1 over b times itself again and again, b times would equal x. Compare this to the definition of the bth root of x. The bth root of x is such that when you times it by itself b times, you get x. We can therefore clearly see that x to the 1 over b is the bth root of x. We are now ready to bring back in the a. We can express x to the a over b as x to the power of 1 over b times a. We can then use the third rule of indices to take this outside a bracket, so we get x to the power of 1 over b to the power of a. This then becomes the bth root of x all to the power of a, and the first part of the proof is finished. However, if we went back to the first step, we could swap the order of a and 1 over b, and express x to the a over b as x to the a times 1 over b. We can then put a inside the bracket and 1 over b outside the bracket to get x to the power of a to the power of 1 over b. This then becomes the bth root of x to the power of a, and we have the second part of this proof. A good example of this would be 8 to the power of 2/3. This is the cubed root of 8 squared, i.e. 2 squared, which equals 4. But it's also the cubed root of 8 squared, which is the cube root of 64 which is 4. I call this going up and going down, and it's usually easier to go down before you go up. It's easier to find the cubed root, or the fourth root, or the square root, whatever the fractional indice is doing, to get a smaller number, before you then apply the numerator in the power to take the number back up. Another example would be 27 to the power of 2/3. This is the cube root of 27 squared, which is 3 squared, which is 9. But it is also the cube root of 27 squared, and 27 squared is huge. You don't want to have to work out 27 squared and then work out its cube root. It's much easier to go down to 3 and then back up to 9 to work out 27 to the power of 2/3. We are now going to go through some of the typical questions that you will get on indices. The first type of question is a simplify question, where you will be given an expression with lots of indices and brackets and so on, and you need to apply the indice laws to simplify the expression. This is really a question of accuracy and having a good understanding of how to apply the indice power laws. Let's look at an example. Let's say we have ab squared all cubed over the square root of 400b squared. We want to go through slowly applying the powers on the brackets in the top line and applying the square root to the bottom line of this fraction. When we apply the power of 3 to the top line, we are left with a cubed b to the power of 6. When we apply the square root to the bottom line, we are left with 20b. Therefore, our next line should read a cubed b to the power of 6 over 20b. We can then cancel the b's, giving us a cubed b to the 5 all over 20. Here's another example. 27b to the 6 over 8c cubed all to the power of 2/3. Give the video a pause now and have a go at it yourself before we go through it. The first thing we want to do is apply the power of 2/3 to both the top and the bottom line. When we have a symbol like b or c to a power being taken to another power like 2/3, we want to keep the 2/3 as a fraction and simply use the indice power laws for one indice to the power of another indice. But when we have a number like 27, which is going to be put to the power of 2/3, we want to write the power of 2/3 as the cube root of 27 squared. Therefore, when we apply the power of 2/3 to both the top and bottom lines of this fraction, we get the following. We get the cube root of 27 all squared, b to the power of 4, over the cube root of 8 all squared, c squared. The cube root of 27 is 3, and 3 squared is 9, so we have 9b to the 4 on the top line. And the cube root of 8 is 2, and 2 squared is 4, so we have 4c squared on the bottom line. The second type of question that you might face is where you have to express one number as some other number to a power. An example of this might be writing 8 root 2 as a power of 2. For questions such as this, you want to write each element of the expression as a power of the number which you are required to write the overall expression to. In this case, we want to write both the 8 as 2 to the power of something and root 2 as 2 to the power of something. Well, 8 is 2 cubed, so we can replace the 8 with 2 cubed. And the square root of 2 is 2 to the power of a half. Therefore, 8 root 2 becomes 2 cubed times 2 to the power of a half. At this stage, we must apply the indice power laws. Because 2 to the power of 3 times 2 to the power of a half is 2 to the power of 3 plus a half, this becomes 2 to the power of 7 over 2, and we're done. The next example we will look at is 27 over the cube root of 9. Here you have to write this as a power of 3. Pause the video now and have a go at it before we go through the method. Okay, so let's write the first line in terms of 3 first. Well, 27 is 3 cubed, so we can replace the top line with 3 cubed. 9 is 3 squared, so we can replace the bottom line as the cubed root of 3 squared. Using the fractional indice law backwards, we can now rewrite the bottom line as 3 to the power of 2 over 3. and the top line stays as 3 to the power of 3. We are now at the stage where we are applying the indices laws. In this case, it's one thing divided by another, therefore we subtract the indices. 3 to the power of 3 divided by 3 to the power of 2/3 is 3 to the power of 3 minus 2/3, which is 3 to the power of 7 over 3. This type of question might also require you to set up an equation for some unknown. Here's an example. What is the value of x if 2 to the power of 2x plus 1 equals 8 to the 7 minus x? The first thing we need to do is express both numbers as a power of the same number. It's easier to express 8 in terms of 2 than it is to express 2 in terms of 8. So we convert the 8 into 2 cubed. We now have 2 to the power of 2x plus 1 equals 2 cubed to the power of 7 minus x. We can use indices power laws to convert the right hand side into 2 to the power of 3 times 7 minus x. We now have 2 to the power of some expression on the left equaling 2 to the power of some expression on the right. Therefore, we can make the two expressions equal to one another. And we have 2x plus 1 equals 3 upon 7 minus x. By expanding the brackets on the right hand side, this becomes 2x plus 1 equals 21 minus 3x. We now have a linear expression, so let's collect our x's on the left and our numbers on the right. Moving the minus 3x across, it becomes positive 3x, and moving the plus 1 across becomes minus 1. So we're left with 5x equals 20. We can divide both sides by 5 and we get the answer for x as x equals 4.